Hi, Recalculus friends. Here we are at the end of chapter 11. We're looking at 11.7, and we're going to be talking about modeling real-world data with exponential and logarithmic functions. So a couple things we need to remember or learn about, and then we'll talk about things we need to remember from the chapter. So first thing is doubling time. So the time it takes for a population, for an amount of money to double can be denoted by this equation here. So the amount of time for a quantity modeled by the exponential equation n is equal to n sub 0, the initial amount, times e to the kt, to double is given with this formula. So if this is the modeling for growth, here is how you will figure out the doubling time. The time will equal to the natural log of 2 divided by the constant k. Non-linear regression. So you might remember linear regression as we would get some data points and we would plug it into Desmos or something like that, and we would get Desmos to give us what we would call the line of best fit, and that line they would give us like a y equals mx plus b situation. Well, we can do that with different functions. I thought we did that with other functions already, but we could also do regression with non-linear equations. So this would be a linear regression if I assume that the data would fall in a linear way. Non-linear regression would look like us considering all of the functions that we've been working on, including polynomials, in order to fit the data. You'll see what that means in a moment. And linearizing data is changing what would be a logarithmic or an exponential function into a linear function, and that's a technique that we'll look at a little bit later. All right? So the first thing we want to talk about is just remember the relationship. Now, when we're modeling equations, or modeling functions, we'll be given some data, and we have to kind of see how the data fits along a particular path and see if we could figure out what the fit is. So let's say we had the data that sprinkles like this. We could say, oh, that looks like a exponential growth function. And so similarly, if we have data that looks kind of like the dots that I'm doing here, you can see that it goes down and it kind of is asymptotic to the x-axis. You can express that as a linear, as an exponential decay function. And so we can see what it would look like in these cases as we're dealing with logarithmic decay and logarithmic growth. So you want to keep that in mind as we're working on some problems. Let's look at example 1. Example 1 is going to refer to the information given in the beginning of the chapter. Latrell, a freshman in Finneytown High School, is given a gift of $4,000 by his great aunt. He would like to invest the money so that he will have enough to purchase a car that costs twice that amount, or $8,000, when he graduates in 4 years. If he invests the $4,000 in an account that pays 9.5 compounded continuously, will he have enough money to buy the car? And so we're going to think about a couple of things here. First of all, basically we want to know how long it would take to double the money. And so we can do this without the little formula that they gave us, or we can use the formula that we were given. If we were to do this without that formula, we would basically be taking $8,000 as the answer to remember the amount is equal to PERT. RT is the exponential values here. R times T. And you can see this looks a lot like the function that we're talking about using to find the doubling function. But here's what we would do. We take the 8,000 and we recognize that the principal amount, P, would be 4,000. We take its E to the, let's get a smaller pen, R. In this case, R is 0.95. No, it's not. Yes, it is. It is 0.095. 0.095 T. And this would be the function that we'd want to solve for t in order to determine whether or not this is true. Well, think about what we would do. We would divide both sides by 4,000, so we get 2 is equal to e to the 0.95 t, right? Then we take the natural log of both sides, right? Because we're dealing with e, and to undo this exponential situation, we deal with the natural log. So we have the natural log of 2 is equal to, now if we do the natural log of this side, swoosh, bam, everything goes away, and we end up with 0.95 t. You understand what I meant? My little swoosh, bam. Basically, this is like the anti-log of e of the exponential relationship e to a power. So we end up with this. Now that we have that, you guys are seeing it. To solve for t, we would divide both sides by 0.095. I'm going to erase that so it looks better. All right, so we get rid of that, and 0.095, that's what we were dealing with here. Let me go ahead and make that work up here too. 0.095 there. All right, all is well. 0.095, and so we get t is equal to the natural log of 2 divided by this rate here. Well, let's go back up here real quick. Remember what we saw? To find the time, it's going to be natural log of 2 times the value up here, whatever that constant is. In this case, the constant was the percentage that would be compounded continuously. So this is our answer, and I guess we should probably figure that out. What interest rate is required for an investment to continuously compound double in 4 years? All right, so we'll check that in a minute. Let me go grab a calculator. So my calculator let us know that it will take about 7.29 years, a little bit more than 7 years for him to amass this amount of money, to double his money at this particular rate. Will he have enough money to buy the car? And so the answer is no, not at the end of 4 years. All right, what interest rate is required for an investment with continuously compounding interest to double in 4 years? Well, we can kind of look at it like this. We know that the formula was the natural log of 2 over that k value is equal to time. And now we know that the time that we want it to be is 4 years. So really what we have to figure out is what k value will work here. So this is a minor algebra problem, right? So if I have a situation like this, I guess I could look at it like this: cross multiply. The natural log of 2 is equal to 4 times k, and then divide both sides by 4, and we can figure out what k is. So again, grabbing my calculator, we get that k is equal to 0.173, goes on a bit. I'll stop there, 0.173 about. And what that means is k, remember k was the percentage written as a decimal, so I'm going to write this decimal as a percentage, and k would, well, I guess the interest rate, because really k is still what it is, would be 17.3%. So in order to double your money, compounding it continuously for 4 years, you need to have it at 17.3%. So here's the problems that we all love to work on. And so what these are those modeling problems where you're going to graph this information on a table. What I would suggest you to do if you don't have a graphing calculator is to go to Desmos, and we're going to put all this information into a table. And I will spare you that by doing it myself and coming back to chat with you. Okay, so here is what we came up with in Desmos, and change the view of the screen in order to fit the points, and so you might have to do that as well. So now that we've done that, let's talk about how we find regression equations. So notice I'm putting in y sub 1. This alerts the computer program that I'm using this information here. I don't use an equal sign, I use a tilde. That looks like this. Let's make it work. Kind of that little wavy line that you sometimes see in Spanish over some letters, and over n actually, right? Anyway, and then, so we don't look at this as a linear equation because we're actually trying to think about what it might be. And you might even think, hey, this looks a little bit like an exponential growth function. And so we would figure out what does an exponential growth function looks like. It's a times b to the x power. And so this x that we're dealing with is to the x of 1. Excuse me. So I'm going to do that. And what I see is that I get somewhat of an answer here. Let me go back. Okay, so I'm looking at this and I'm thinking, oh, this doesn't actually fit as well. And so I see that Desmos has this thing called log mode. And when I click on that, that fit seems to curve a little bit better. I don't know. What's your impression? So, you guys can let me know what you think So I looked up what log mode was, and they have a kind of a complicated explanation that it shares with us a little bit of information about why Desmos doesn't do log mode initially, but what I'm finding is that log mode is going to give us, as we look at log mode here, it's giving us an answer that your text came up with using probably a TI-82 graphing calculator. So this is more aligned in terms of numerical values with the values that you'll get from the textbook. So using log mode would be helpful when you're doing your assignment, all right? So that's what we got. So the function, I'll write down the function that we got. So this is the equation we get as we try to find that function. So we realize that Desmos gave us the A value and the B value as we did exponential regression. So using this equation, we're supposed to use the equation to predict the population of the world in 2050. Now we remember that we were doing this from 1900s, so that's how we're calculating our timeline. And by the time we got to the year 2000, it was 100. So if we're going to keep going to the year 2050, we're going to get to 150, right? And then so that's what our x value will be. So we're going to plug that all in. And so instead of having an x here, we'll raise it to the 100 and, not a great pen, we'll raise it to the 150th year, and that'll be easy to do. Over in Desmos, I'm getting 11.11 billion people on the earth by 2050, according to this calculation. So here in example 3, we have another situation where we're going to put this information in the calculator in Desmos. An ice skater begins to coast with an initial velocity of 4 meters per second. The table below gives the time required for the skater to slow down to various velocities. Find an equation that models the data. So we're going to plot this information in Desmos, and then we'll do some kind of regression. So putting this information into Desmos, as we see here, let's see if we can get it back into view, changing the screen a little bit in order for us to see the points. This is what we have. And so when I did it, I got this value here. I did, it looked like an exponential. And so I said, okay, fine, this works out. And we have a pretty good fit. Your textbook said, had a different answer. And I don't really know that it would make sense for you to do this, but I want to show you that you can do it anyway. Is this answer fine? Yes, it is. I mean, you're asking the calculator to do a regression based on the data there, and you can see that we hit a lot of the points. So that's really good. But your text chose to see this as an exponential, as a logarithmic equation, which is not a natural thing for you to see, but let's see how we could do that. So if I were to start off by saying y sub 1 is, we're trying to make it equal to some value a such that I can add that to b times, let's say, the natural log of x. Okay, now remember we have to do x sub 1 in order for the calculator to recognize that we're talking about the data set above. And when I do that, we get, and this is what the textbook actually had as an answer, and I'm going to zoom out a little bit so you guys can see that also the green equation fits very well. So you can see that there's more than one way to describe a data set, and so this is the way your text chose to do it. This way would be absolutely fine for our intents and purposes. And I'm wondering if the restriction of technology or the newness of the technology that allows for such contouring of data, led the textbook to feel like there was, or the textbook authors to feel like there was one specific way of doing this. So this is what I would do with this data. So here are the two equations that, the one that I got and the one closer to what the textbook got using natural log. Now we turn to the idea of linearizing a function. So first of all, where does the concept come from? Well, let's say we had y is equal to a times e to the bx. This is kind of a typical generic exponential equation with base e. We can take the natural log of both sides. So the natural log of y would be equal to the natural log of this product of a times e to the bx. Given our log laws, we know that we can rewrite the natural log of y in this case as the natural log of a plus the natural log of e to the bx. Following with our log laws, we continue with the natural log of y being equal to the natural log of a, but this time plus bx times the natural log of e. You know that the natural log of e goes away, and so what we actually have here, natural log of y, that's a number, is equal to the natural log of some constant a plus b times x. This is a linear equation. If you think about it for a moment, you can see that it is a linear equation, an equation with the variable x. So this concept is going to give us the ability to work on the following problem. So let's get back to our problem here to see if we can utilize that concept. So the Consumer Price Index, CPI, measures inflation. It is based on the average prices of goods and services in the United States, with the average for years 1982 to 1984 set an index of 100. The table below gives some CPI values from 1950 to 1996. So we've got our chart. We're going to plug it into Desmos, but here it says linearize the data. And in this case, that is make a table with x and natural log of y values, where x is the number of years since 1950, and y is the CPI. So what we're going to do is we're going to be taking the natural log of each of these as our y values. And then for the x values, we're going to use years since 1950. So that would be 0, 10, 20, 30, 40, and 50. So let's go ahead and put that in Desmos. So here's the data we get when we plot it. And I love Desmos because it allowed us just to put natural log of 24.1 as opposed to actually putting the values in there ourselves. And so now, since we have linearized the data, we're going to do a linear regression. So that's going to require me to do y sub 1 tilde is equal to mx sub 1 plus b. And so we get this equation here and that's going to be our answer for part B, I believe. So the first thing, linearize the data. That is, we did that. We put in a scatter plot, find a regression equation for the linearized data, and that's what we have here. So again, let's get rid of that. M value is going to be, the slope is going to be 0.041644, and the y-intercept is going to be approximately 3.05364. Okay, so now that we've done that, we're going to use the linear regression equation to find an exponential model for the situation. So let me write down that linear regression equation for us. So really, this is the equation. Since we didn't actually relate y and x, we related the natural log of y and x. We've got the natural log of y is equal to that. So we're going to use the linear regression equation to find an exponential model for this. So the equation is given as such. What we're going to do is now solve for y. And in order to solve for y, what we're going to do is raise both sides to as an exponent of e. And that'll definitely take care of that. Let me finish writing this down, 364. So if I raise this to the e power, I'd be raising this side to the e power. Are y'all with me? You see how we did that? Okay, so then this side we end up with y, because e to the natural log of y is just y. And then here we get e to the this power plus this power. And if you think back to your exponential laws, that really means e to the, I'm not saying all their values, but e to the 0.041644 power, 1644 x power times e to the 3.05364 power. And so by figuring out what e to this power is, it got approximately 21.19. We get this equation, which is an exponential equation with base e. And so that's what we have. We did the transformation. Now we're going to use the exponential model to predict the CPI in 2020. And so if we had to do that, we need to remember that we were counting from the year 1950, and the x value or the time value that we'd be using would be, I think, would be 70 years. And then so when we plug this into our calculator, the answer that we get, I'm getting approximately 391 as that CPI value for 2020. All right, guys, I hope that this makes sense and that you're ready to try some of these types of problems on your own. It is a lot of calculator entry and putting information in and using the regression function. So it's not a whole lot of work on your end, but enough work to keep you busy. All right, let me know if you need any help. I look forward to talking to you all soon. Take care. Bye-bye.